Hey everyone, my name is Smriti, and today I'll be walking through the week 11 worksheet, problem number 4, insert meme here. So this problem can actually look a bit confusing at first, just because of this huge table with a lot of numbers in it. And so that's why I want to walk through this problem so that you are pretty clear on how we arrive at the solutions. Cool. So to get started, let's first look at the format of the problem. It's not like other problems we see on these worksheets typically. So on the left side here, next to the green line, we can see a bunch of numbers, and these are all actually indices for a list. So we start out with this list. Let me highlight it. Let's choose this color. So this is our original list that we're starting out with. And at the first index, you have the number 4,873. At the second index, you have the number 1,874, and so on. And so this is our list. It's vertical instead of horizontal, like lists are typically represented, but that's completely okay. And then A, B, C, D, and E. So this part, these all represent different sorts. So this list is being sorted, and they've basically taken this list at a random point during a sort and just put that list here. So this is at a random point in one of the sorts. So is this, and so on. So our goal in this problem is to essentially figure out for A, B, C, and D, each of these, and E, sorry, which sort resulted in the array below this letter. And what makes this problem especially challenging is that this isn't the completed, well, the completed sort would obviously be sorted. So we would end up at this list at the end, right? But these are all like in the middle. So we really have to understand how each of these sorts works in order to arrive at an answer, because these could have been taken at a random time step during the sorting process. Cool. So let me erase all the extra lines. Hopefully that made the problem seem a little bit more clear to approach. So the first thing I'm going to do when looking at this problem is I'm going to look at the sorts that I'm trying to find here. So two of them that really stand out to me are LSE radix sort and MSE radix sort. I like to do these ones first because I think personally that they are the most simple to identify, because for MSD radix sort, we are trying to look for a list that has the most significant digit all or mostly sorted. So as a quick refresher, MSD radix sort basically sorts by the most significant digit. So if you have like a couple numbers like, I don't know, 2, 5, 6, 0, 1, 4, 9, it's first going to look at this digit, right, the most significant digit, and it's going to sort the numbers based on that. So since 1 is less than 2, it'll bring this number ahead of that one. And it'll look at the second digit, and it'll look at, oh, is 3 less than 5? Yes. Is 4 less than 6? Yes. So it's going to sort by the most significant digit. Cool. All right. So when I'm trying to find which of these is MSE radix sort, I'm basically looking for the most significant digit, which is this first one, should be sorted. So in A, I don't see that. It's going 1, 1, 2, and then I see a 1 here, so it can't be A. In B, I see 1, 1, 1, 2, 3, 4, 4, 6, 6, 7, 8. Oh, this looks sorted to me. So here we can see that our most significant digit for B is sorted in ascending order. And so I am going to say that B is MSD radix sort. Cool. solid. So the next one I want to look at is LSD radix sort. For LSD radix sort, the key thing to note here is that this is just we just want to look for a list where at any point the digits are sorted. So it could be any of the digits. It might not necessarily be the last one. It really depends on where you are in the sort. And so just one of the digits to be sorted. So let me write that down here. Cool. So I'm going to start by looking at the rightmost digit and then check the second from right. And then I'm going to keep going until I reach basically the first digit and see where I have one where something is sorted. So let's see. I've already classified B, so I'm not going to look at B anymore. Let's go back to A. Are any of these digits sorted? So 6, 4, 2, that one's not. 7, 7, nope. 8, 8, 2. So I'm going to rule out A. A can't really be an option. Actually, instead of putting an X here, let's put like a check mark so that we know we've classified B. Okay, cool. So then I'm going to move on to C, where I can see that 6, 4, 6. Yeah, none of these seem to be sorted, really. I guess the first one looks sorted until we reach here where we see that we get back to 1. So that one is not sorted. So no, not C. Let's look at D. 3, 1, nope. 7, 2, 3, nope. Because we go back to 7 there. 5, 1, 1, 9. Those are all not sorted. Then let's look at E, where I see 2, 7, 1, 6, and that's not sorted. 1, 1, 2, 2, 3. Oh, this looks pretty sorted to me. 5, 7, 7, 7. Okay. Cool. So I see here that the second to last digit in E is fully sorted. And so I'm going to classify E as LSD radix sort. Cool. Now that I've done LSD radix sort, I'm going to move on to, let's see, which one should we do next? Let's do quicksort next. So in quicksort, we use a pivot strategy, right? So let's look at what the pivot strategy is. Okay, so they're choosing the topmost element as your pivot. And then they are using, okay, cool. So if we run quicksort using the pivot strategy outlined in this problem, then we need to basically check that once we do our partitions, the topmost element is in the correct final position because we're going to be using that as our first pivot. So if we look at any of these problems, or not any of these problems, any of these rows, or actually I should say columns, these are all columns, right? We need to find one where 4873, our initial pivot, has been put in the correct place, because in quicksort, you're basically, if you're given a list, right, like, let's see, 1, 2, 3, 5, and maybe I should put one that's less, 0. First is going to look at 1 as our pivot in this pivot strategy where it takes the topmost element. Actually, let me redraw this so that, okay, 1, 2, 3, 0. So in quicksort, I'm going to go through, and then anything that's greater than 1, I'm going to keep below it. And when I reach 0, I'm going to actually put that to the other side. So it's going to look like 0, 1, 2, 3. And then I'm going to sort this side, and I'm going to sort this side. But the key thing that we need to know is that our pivot, our initial pivot, will be in the correct position. So when we look at 4873 in our list here, it should actually be in, let's see, 1874. Basically, everything after 4873 should be greater than 4873, and everything less than 4873 should be in front of 4873 or above 4873. So for part, let's look at A here first. Cool. 1876, 1874, 2212, 166. Okay, so all of these elements are less than 4873. So this seems to be in the correct position just based on the top elements in this list. Let's look at the bottom and see if those also work. 9573. Okay, yeah, so these are also all greater than 4873. So since it's like my pivot is in the correct position, I can assume that A is quicksort. Just because let's look at 4873 in the other list that haven't been classified yet. So 4873 is up here. In this one, let's see, it's down here. Yeah. Oh, 4873. Oh, sorry, we already classified E as LSD radix sort, so it can't be that one. So we see here that in C and D, the other possible options, it wouldn't be possible for it to be quicksort because on the first run of quicksort, we're going to put 4873 in its proper position because that's our first pivot. And we're going to sort around that. So it has to be A. So I'm going to set A. Let's check it off and set it to quicksort. Sorry if this is a little confusing. Let me clean this up by erasing this. Cool. And I'll draw arrows that we know exactly what we're talking about. All right, so now all we have to classify now is C and D. And so what we have left, we have merge sort and heap sort left. So in heap sort, if we take that one next, we know that heap sort, we're using a max-oriented heap. So if we're using heap sort in a max-oriented heap, like if you were to draw a heap out here, right, you're going to have your largest element in this bubble, and then your second, like everything smaller than that is going to be below. So we basically need to look for a list where it has all of the larger elements on top. They might not necessarily be in sorted order because in a heap, the only requirement is that the children are less than the parent in a max heap anyways. So we just need to look for between C and D, which one has like the bigger elements pushed to the top, like it was inserted into a heap. So here, I straight off the bat, I'm looking at the top of D and I see like a lot of big numbers here. And so I'm going to assume that D is heap sort and not C because C seems to have a lot of smaller numbers at the top, which doesn't look like they've been inserted into a max heap and converted to a list. So yeah, keep in mind that not all of these will be perfect because we're taking it at a random step in the sorting process. So it's not fully sorted yet, but we can see that at D, we're pushing it to the top. So the top element is our next max element. And then at the bottom, we should have a sorted order because in heap sort, that's how it works. We push the next biggest element to the top, and then we basically are going to be sorting from the bottom. So if we look at the bottom here, we see that it is in sorted order. 1, 1, 1, 1, 3, 4. And these are probably the next elements that are going to be pushed to the top after that. So yeah, we can see that this is heap sort. All right. So the last one, we can probably by elimination also say that C should be merge sort. Make this smaller. I put merge sort here. But let me also explain why it should be merge sort. So in merge sort, we said we use a recursive top-down implementation of merge sort. And we basically are going to fix items in groups of 2 in merge sort. So what it does is it takes this huge list, right? And then it'll break it down. And then it's going to basically sort either side of it. And it's going to keep breaking down your list until you get to single elements, and then you're going to put them back together in merge sort, right? Sorry for this very crude drawing. But that's basically how merge sort works. So we're going to look for sorted runs where basically it has been partitioned and split into like little chunks, and then those chunks are being sorted basically. So in C, we can see that we have little runs of sorted elements that might not necessarily be the entire list, but you can see that like smaller parts of this list, like the sub lists, have been sorted. And so that's why we can say that it's merge sort. Yeah, this is probably, it's probably been partitioned into groups of 4. So we can see here that it's been split up into smaller parts, and then those individual parts are being sorted before they'll be merged at the end. And that's why we can say that that is merge sort. Cool. And so with that, we've classified A, B, C, D, and E with their sorting algorithms. As you guys can see, it can be very confusing to approach these problems. So definitely don't worry if you didn't get the right answer at first, because a lot of this stuff is a little bit arbitrary and you really have to understand how the different sorts work to identify a sort in the middle of the sorting process. But definitely with practice, it'll get better. And just understanding like how each sort works and like the steps involved will definitely help with problems like this. Cool. So if you have any questions about anything we did today, definitely reach out to your CSM mentor. But otherwise, I'll see you guys at the next walkthrough.